I'm Karen Schwartz, a longtime writer for ITPro Today covering storage and cybersecurity. Let me introduce you to today's speakers. JB Baker is a member of the Storage Networking Industry Association's Computational Storage Special Interest Group, as well as a marketing and product management executive at ScaleFlux. Steffen Hellmold is a member of the DNA Data Storage Alliance and vice president of strategic initiatives at Western Digital. Today, we'll be talking about how companies can keep up with the unprecedented growth and types of data, focusing on some of the most promising and innovative approaches. So to set the stage, what would you say is the state of mainstream storage in the data center today? Steffen?
Sure, yes. First of all, Karen, thank you for having me. I would say we can say that today the majority of data is served with hard disk drives and with SSDs within the data center. And as we look into that pertaining to hard disk drives, we've come a long way from the innovation perspective, right? 65 years of development from the initial inception. We are today at 18 to 20 terabyte storage capacities as we're looking into the mainstream of SSDs, right? When we go back to that journey to 1991, when the first 2.5-inch SSD was introduced, we are at about 8 to 16 terabyte for mainstream. We are seeing capacities all the way to 100 terabytes as on the high end of builds. That gives you a little bit of a flavor of what are the main tools in the toolbox that we have today. Certainly a tremendous scaling. When you think about that, the first hard disk drive was 5 megabytes and the first SSD was 20 megabytes when originally introduced. So with all of that said, the storage industry is in constant race to continue the scaling, to keep up with the ever-growing data storage demand.
So that presents probably some real challenges for organizations around data. I mean, there's so much of it. What are some of the biggest challenges that organizations today are facing around data? Maybe JB can take this one.
Sure. As you mentioned, this volume of data is one of the key challenge, or is generating a lot of the challenge. But it's not just the volume of data, it's also the pace of the data and the security around that data. You hear a story almost every week about some kind of security leak or intrusion that grabbed a bunch of data or allowed a system to be locked down and have to be ransomed or something back. So securing the data, securing the network is a huge challenge. And then that pace of data, Steffen mentioned the rapid increase in the density of the storage devices themselves. But then on top of that, we've had massive increases in the speed that these devices can serve the data. So, you had hard drives and then SATA SSDs that could do hundreds of megabytes per second and SAS SSDs at a gigabyte per second. And now we've got NVMe SSDs today at over 3 gig per second and rapidly transitioning to 6 and 12 gigabytes per second. So it's how do you deal with all of that speed as well as the massive data that creates massive challenges around how do you scale your processors, how do you scale your networking bandwidth, how do you scale the power supply to move all this data, and then the IT and facilities infrastructure to help you convert all of this into information instead of just raw data. And then all that while you're trying to stay on budget. So it's a very big challenge for the teams that have to manage the IT infrastructure.
So this sounds like a pretty big deal for companies. It sounds expensive. It sounds disruptive. Well, let's back up a little and ask about, so how are the typical approaches of storing data falling short today? And then we could follow that up with maybe some ways that they can upgrade their storage or improve without ripping and replacing and breaking the bank. So let's start with, how are the typical approaches of storing data falling short?
All right, I'll go first. So I see a lot of them are just really not optimized around the advances that we've had in the storage technology, particularly that pace of data that I mentioned. I think there's still a lot of approaches to data that are tied to the legacy of hard drives and the latencies and the bandwidth that can be supplied by those hard drives. And they really haven't stepped up to fully taking advantage of flash, and particularly NVMe flash, which is the fastest, widest bandwidth. And then within NVMe, there's additional features that are coming out into that protocol to further optimize that protocol for accessing the data and managing the data.
Yes, and to add on to that, part of the challenge is that today we have the vast majority of data stored on HDD, right? And that's complemented by flash. So think of it, about 10% roughly of the data is on flash and 90% is on HDD. And the architecture of blending those two, right, with SSD being for hot data and HDD being for cold data, if you just look at it very simplistically, right? Evolving that with evolving workloads, right? And to the point of what JB was talking about, right? Processing the data in the ideal location. That is really where the challenge is as workloads continuously evolve, and it'll be increasingly impossible to move all the data to the compute, right? But you have to find ways to blend general purpose compute with purpose-built compute, right? And process ideally data where it is located.
So I hear a lot and write a lot about hyperconverged storage and hyperconverged infrastructure, and how that seems to be a good first step for a lot of companies in getting their arms around it. Would you agree that is that sort of a table stakes kind of thing today, or just one approach?
It's one approach for sure, and it definitely, as you go back to a hyperconverged style, you're able to avoid some of that bottlenecking on the network and the latency of transferring the data across the network by having a significant amount of application processing that is co-located or can be, you can send that task to the system where the terabytes of close data are stored. So that can help alleviate some of that transfer of data across the network.
Yeah, and then if you look into, for example, hyperscale deployments, you'll find also tiered storage, right, as well as disaggregated storage deployments, right, as tools, right, where each hyperscaler has their own proprietary architecture on how to best parse the data basically across all the fundamental functions from storage to compute, right?
Okay, thank you. Now I wanted to talk about two kinds of storage technologies that people may have heard about, but probably don't know much about. If you could explain them briefly and kind of explain when they might help, what their best use cases are. One of them is computational storage, and the other is DNA data storage. They both sound a little science fiction-y, but I think they're here today. So computational, I guess we'll start with that. I think, JB, that's your area, right?
Yeah, so it's gonna be hard for me to stay brief on this one, but
Okay.
But computational storage is an architecture that is an effort to offload some tasks from the central processing unit, or reduce data movement to alleviate some of the bottlenecks I've talked about on whether the PCIe path or the network. So, I mean, at a very high level, the goal of that is to improve the efficiency of your infrastructure by reducing how much you have to move the data around, and then get rid of that bottleneck at the CPU, because we've seen the pace of growth of CPU performance slow down while the pace of bandwidth in data has just continued to increase. So there's a couple of ways that you might utilize computational storage. Our first example would be in that offloading of a task from the CPU. A task that is not done very efficiently by a general purpose CPU is compression. It can consume a ton of CPU cycles and percent of your CPU to do that compression task. It can be performed much more efficiently in a hardware engine, either in a computational storage processor or directly down in the computational storage drives. And just to nail that home as an example, what we did some testing with Intel Xeon cores and running like gzip on data there, and we found that they only got about 50, 60 megabytes per second of throughput, megabytes per second. In one computational storage drive, we're able to get over 2 gigabytes per second of compression throughput and 3 gigabytes per second of decompression throughput just in that drive by adding maybe 1 watt to the drive. So to that balance, like 47 Intel Xeon cores running at 10 watts a piece and costing you a pretty penny versus a 1 watt in a computational storage drive to get that throughput for your compression.
So what's the catch then? Is it super expensive? Is it a rip and replace situation for companies? Why wouldn't everybody want that then?
There are certainly instances where their compression is not a bottleneck for them. But yeah, I mean, we kind of question why everybody's not doing it today, except for that computational storage is still relatively new and just hasn't hit that full mainstream adoption yet. But we do see that over the coming few years, you're going to see more and more of this functionality get pushed down into computational storage drives and computational storage processors.
So what would you say would be the biggest use cases?
Yeah, so a huge use case for computational storage drives today is around accelerating databases. And every major corporation, every enterprise deployment has databases in their deployment. And anytime you're pushing for a high performance database, the computational storage drives can help by delivering better latency profile than ordinary NVMe SSDs or SAS or SATA SSDs, or it's kind of orders of magnitude better than hard drives, as well as then potentially saving you cost by storing more data per drive by performing the compression task in an extremely efficient way, power efficiency, space efficiency, and then cost efficiency as well. And it's not just compression. There's other functions that can be deployed that become a little more nuanced or application specific, like data filtering. And that would go back to more the disaggregated storage, where you want to alleviate how much data you're transferring across the network. And if you do some filtering of that data to perform a query, say right down in the drive, then you can cut the amount of data that you have to transfer across the network by 90% or more, right? And then you're also alleviating the CPU burden, because now the CPU doesn't have to sort through terabytes of data. Maybe it's just gigabytes of data to sort through to perform the complex aspects of the query.
One more question before we get a little overview of the DNA data storage is, what would this replace in a typical storage environment?
Computational storage drives are really going to go in and replace your ordinary SSDs.
Okay.
They're the same form factor, same power envelope, all the same protocol. So it's just leveraging those existing storage bays to increase the value of the storage bay and increase the value of your system.
Great. So DNA data storage, I'm sorry, when I think of DNA, I think of 23andMe, and this can't have anything to do with that. So what is that?
Yes, let's start off with why do we need DNA data storage? I think that may be helpful.
Okay.
And I get into what is DNA data storage. So the Semiconductor Research Corporation had determined that based on the demand, as we're looking throughout this decade, right, we will exceed the capabilities of scaling of existing tools in the storage toolbox, namely HDD and SSD, right? So maybe we can get an order of magnitude scaling out of both, but the problem is per the SRC, that the goal is, or the aspiration or the need is, that we need to find something that can scale 2 orders of magnitude or more for basically areal density capability to deliver the capacity to store all of that. And that is predominantly driven, if you ask me what's the key use case, it's the archives, right? It's the archives that are growing and growing and are further projected to grow even further. And also the cooling of the data, right, is basically making us seek for new additional tools in the storage toolbox, right? So that's where the need comes from. So then as you look into, okay, what candidates are on the horizon that could actually meet such a need, right? And you go through the list of possible solutions, right? The only thing that comes about is DNA data storage. And DNA data storage is modeled after basically nature. It is simply an approach where you are generating DNA strands out of ACGT, right, through a biochemical process where you are encoding data into DNA. And then you store that, right? The benefit of that is it is extremely dense, right? Much denser than any other storage technology today. It is very, very long lasting. It has very low power and can overall from a TCO model be extremely attractive. Now, the one thing on top of it, as if your head is already spinning on DNA data storage, I'll add one more for you. It is possible because of the biochemical tools to perform actually computational operations into DNA, right? So one example would be PCR, right? So with a PCR primer, you can actually search into DNA data storage. Now, one DNA with the biochemical processes, you go fully parallel. So seeking something within you search for something in a zettabyte of data stored in DNA may actually be quite fast, although, right, DNA data storage by itself is certainly much slower than SSD or HD. But if you can go parallel, right, then you actually could have, for very large archives, a speed advantage when you're searching for something, that especially something that you haven't prior indexed, right, where you have to crawl through everything and you have to read everything to find it.
So, well, give me a couple of use cases where it would make sense today.
Well, people are talking about use cases that you will find already in the current deployments. One is if you think about video surveillance or smart video, as well as if you think about autonomous driving, right? And one of the interesting use cases is actually in the store it and retrieve it upon subpoena. They are kind of like legal archives. Think about it, right? Like where you have to prove that the car that was involved in an accident has been making the right decision, right? Based on the autonomous driving call. And the problem is now you have to retain all of the data that you use to train that algorithm, right? And it could be quite costly and you may never need it, right? If there's never any problem. So you would want to store it somewhere and you got to be low cost for a long period of time. You don't want to have to ideally migrate data. So DNA data storage is ideal for that. The same for when you think for surveillance, right? When you have vast amounts of video that you want to go and preserve, right? And at some future point, you may go back, right, to retrieve some special thing of interest, right? That is something that you can realize with DNA data storage as well. These are kind of like use cases from mainstream archive, basically usages that are already on the visible horizon today. There are other use cases. I give you one that is a very small amount of DNA is the coding of medical tablets with DNA's data storage in the film actually that codes the tablets, that gives you the entire history of what is all in that tablet, where was it made, right? The entire supply chain and production history. So if anyone just picks up a tablet today, you can't tell what it is, right?
Right.
But if you had a coding with basically DNA data storage implemented, right, in that coding of the tablet, you could retrieve all the information about that tablet that you have in your hands, right? That's, again, another use case that is already in the process of being commercialized as we speak. Now that the amount of data is much smaller, right, than the other use cases I mentioned.
So how widely used is this today? It's still sort of at the beginning, right?
Yeah, I would definitely say it is at the beginning, and there is a major effort underway through the DNA Data Storage Alliance to build the ecosystem, right? There has to be interchangeability, there have to be standards generated going forward. There has to be an opportunity for all market participants, right, to go and produce as well as retrieve data, right, from DNA data storage, whether they do it directly or it's done as a service, right? There are multiple deployment models there as well. So Gartner was given indication that they're expecting that by towards the middle of this decade, they expect a number of basically companies to run trials on DNA data storage. So if I was looking into my crystal ball, I'd say, sometime within the first half of this decade, we will see initial commercialization of DNA data storage, right, at an initial market scale, which then will, in the second half of this decade, right, get to kind of like the large scale of commercialization.
So these things, computational storage and DNA data storage, these are huge changes, huge shifts. And your typical company is probably not even aware that they exist, much less interested at this time. So if you were to both look out, I mean, I'm trying to get my hands around when these things might be mainstream and what they might replace eventually.
Oh, that's a good one. If I can go first, Karen, this is always my favorite question. And I always, having worked also in SSD before, I said, don't try to kill HDD because you're going to kill yourself, right? It's often not about displacement. It's often about adding, okay? And then will there be cannibalization? Yes, right, there will be. But so naturally today, tape is used, right, for archive as well as disk, right? Will there be some cannibalization? Probably. But when you look at the characterization and the basically the value proposition of DNA data storage vis-a-vis disk and tape, right, it's vastly different, right? So I would think that the majority of DNA data storage is going to be net new, right, with some cannibalization into tape and disk.
JB,
I'll let Steffen's comments stand on the DNA storage. I'm not as nearly as well versed as he is in that. On the computational storage, you're right. There are, it is a change, but some of the aspects of computational storage, some of the functions that can be deployed there can be transparent and extremely easy to adopt. And as I mentioned before, it's just it plugs right into the slots where people plug NVMe SSDs today. So aspects of it can certainly be extremely easy to deploy and adopt and get the value out of. And it's not really replacing NVMe, it's adding on capability to those slots and bays. And then there are going to be additional capabilities that come out that will require some software modifications and require some file system advances to take full advantage of. And those will take a little bit more time. But just as Steffen mentioned on the DNA side, there's industry organizations working on the standards. We've got that working with SNIA, Storage Networking Industry Association, on computational storage, as well as efforts within NVMe org on how do you work with computational storage devices. So I think we're rapidly coming to the early mainstream of that. We've already got early adopters and multiple products out from ScaleFlux and others on the computational storage side.
So, but in the end, companies want plug and play.
Yes.
Right? Will we get there on these types of technologies?
We have to. If we want to deploy it at maximum scale, right? Ease of use is very important, whether you look at computational storage or DNA data storage, right? You have to, in a perfect way, exactly as JB said, make it transparent and expose the additional features in an easy to use fashion.
Yeah, exactly. And we're definitely getting there. And for some functions, like I said, it's there very easily. Others, it's going to take a little bit of time to make that transparency and ease of use just plug and play.
Right. So these are two really interesting types of upcoming storage solutions, but there must be others. What other techniques could make a difference? Both, well, let's split it up. What can companies do today, or IT staffs do today, to sort of optimize their data storage? And then in the future, well, let me ask that first. So what can they do today, backing off from the computational storage and the DNA storage for now? What are some techniques they can use today other than maybe adopting a hyperconverged infrastructure?
There are some, capabilities today, and I can't back off of computational storage, but like the easy to use parts of computational storage today, and also newer technologies like persistent memory, that both of these can help alleviate some of those system bottlenecks and improve the efficiency of the systems to get more work done per 2U server or rack server. So, I mean, those are some key things, and then just really managing those tiering and identifying what your workload is, what portions of your data are critical to be hot, and what data can be archived and moved to the colder storage.
Yeah. And just to, this is a perfect segue, Jay, I really appreciate it, because Karen, where I find where the biggest problems are that we're facing is actually understanding what data is how cold or how hot, right? I mean, you've stored something on a media, right? But that doesn't mean that that media is the best choice, right? So the question is, right, what's the SLA that you need for what share of your data, right? So what share of your data do you maybe never touch again? If the answer is 60%, then, well, if you can identify that 60%, right, what it is, right, that could save you a lot of money. I mean, that is where I think when you ask the question, it's an excellent question. What can organizations do is improve the understanding of what data you have and what are your needs to access that data over time.
Well, I wrote an article recently about sort of the warm data phenomenon, where data sort of, even if you're not going to use it often, that with all the big data analytics that are going on, there's always the need potentially to access all kinds of data. So how does that warm, the need for most data to be warm fit in?
No problem. Again, so think about the following. You have a set of photos, right? 10 years from now, right, anniversary comes up, right? So now an operator that stores your photos, they want to go retrieve those photos, process those photos, and then go send you some advertisement, right? So over maybe the first, let's say 30, 60, 90 days, or the first year, the data cools down when it originally was acquired, right? The picture data. Then it's stored maybe for 10 years and it's cold, right? But then it becomes warm again. So the architecture must allow for the ability that data that got cold over time, right, that if it gets hot, right, you pull it back out of the archive. That's why the tiered structure that JB mentioned is so important, right? And then after 10 years, it can be hot for a couple months, right? And then it cools down again, it becomes cold data. It's just the problem, Karen, is that if all of your data is hot, right, and all of your data is stored on very low latency storage, then the question is, are you prepared to pay the bill for that?
Right, of course.
Right, that's the problem.
When money, right?
To add on there, we do now. There's multiple grades of the media as well. So now, over the last couple of years, we've started to see QLC media come out for NAND, which, if you're not super familiar with NAND, it stores more data per cell on the flash, but you can't rewrite the data as many times, and it has some additional latency versus the less dense NAND. And we're going to see 5-layer or 5-bit per cell data NAND coming out as well, and that's going to have additional kind of degradations in some of those capabilities. So being able to recognize the parts of your data that are maybe going to be write infrequently and read often. If you're writing this set of data out there and then you want to run a bunch of analytics on it, you don't necessarily need to rewrite it, but you do need fast access to it, right? And so you want it on that flash tier, but you don't want it on the most expensive flash tier because you don't care about that endurance and rewriting the data very, very fast.
Okay, I want to go back to that point about not breaking the bank, because money talks. And what are some ways that companies can improve their storage infrastructure and situation without spending a ton? I mean, is it possible?
Yeah, it absolutely is. Particularly if you, from the last question, if you're paying attention to which portions of your data are super hot or which applications require super hot data, and then just sizing those tiers appropriately. So if you've got very high transactional or high performance transactional database where you're doing fraud detection and electronic commerce, electronic payments, and that has to be super fast, you need flash storage in there, and probably the fastest flash storage you can get. And then there are means even within that, like we mentioned, of performing compression on that data in a very efficient manner so that you can then reduce the cost of storing it by storing more data per byte of flash that you purchased. And then that further understanding of the data that says, oh, I've got this other application that doesn't require that fast access, being able to move that off to the QLC or the hard drive or even tape, or in the future DNA, then understanding that can help you manage your costs.
Yeah. And I think what is very important, Karen, is that it's an ongoing exercise that you have to go through that overlays your temperature profile of your data with what are my storage options at a given point in time, right? And because technology is advancing so fast, right? You can't make this an exercise that you do every 5 years, right? You have to constantly observe, right? What are the latest technologies that are available that could basically give me an advancements, right? In cost, and there are plenty of advancements even within SSD and HDD, right? That would allow you, again, if you understand the temperature profile of your data well, to optimize cost, right? With what we have today.
Well, let's end with this then. What can companies do in the next 2 or 3 years to prepare for these really up and coming technologies and processes like computational storage and DNA data storage?
You want to go first?
Sure. Yes. For DNA data storage, I think it's very easy. Is think through the possibilities, right? Think through what are your use cases, right? When you look at DNA data storage, right? And you have an initial projected basically profile of what DNA data storage can deliver, right? From the value proposition. Think where in your organization, right? Would that be something that meets your needs, right? And then engage in, to the extent possible, trials, right? It's always, when you think about it, when the first SSDs came about, nobody knew how to build the best system with SSDs because nobody had done it before, right? So only through trial and error, you'll find out. It's the same for computational storage. Go ahead, JB.
Yeah, and I'd say that you definitely want to really be digging into what are your true pain points. You maybe can solve a problem of scaling just by adding more servers, but now did you really, you solved the processing problem, but maybe now you created the networking problem. So, really taking a look at how much data you have, how much you have to move it, and then understanding those pain points in your deployment and for your applications so that you can then decide, do you want to scale up or scale out? Do you want the disaggregated storage? Is a hyperconverged going to serve you better? Because there isn't going to be one solution that fits every use case.
Right.
And also we've got edge deployments growing, and edge can mean a lot of different things as well. So you've got to really pay attention to what are the compute, storage, and networking needs at each of your different deployments.
There's a lot that goes into storage these days. It's certainly not the sleepy area of technology that it used to be, for sure. Any final thoughts? Otherwise, I'd like to thank both of you very much for taking the time to explain these techniques, and to the audience for listening.
Sure.
You're very welcome. Thank you for having me.
Thank you. And we're happy to take additional questions from the audience and help answer their questions there too.
Thank you.
Yes. Thank you.